Hello guys, in this video we are going to be discussing control block diagrams, and this is one of the very first things you're going to be learning in a process control class. And at the high level, what we are essentially trying to do is take a process. It can be something as simple as water inside of a tank, or a very complicated thing such as a exergonic chemical reaction. And what we're going to do is we're going to model this system as essentially this black box, and we're going to begin to look at the inputs we have going into our process and the outputs of this process, and how can we begin to design logic and have a controller that can help us make use of this process to drive some kind of utility for society. And so at that level, to me, this is pretty exciting stuff, and I hope that this video helps you guys out when you are getting introduced to this subject. And so we have two kinds of inputs going into our systems when we begin to look at these things as process engineers. So to the left here, I have some kind of generic process, and we have manipulated inputs. These are inputs that we can directly control, as well as disturbance inputs coming into a system. And sometimes you'll have no manipulated inputs or no disturbance inputs, and that's perfectly valid as well. Coming out of our process, we'll have some kind of measured outputs and unmeasured outputs, because we can never fully define a system, as we learned from quantum mechanics. And so when we begin to strap controllers into this process, when we want to, for instance, regulate how quickly a chemical reaction is occurring inside of a CSTR so that we can make sure that we don't get a runaway reaction, the high-level diagrams that we begin to draw look like this. So with our manipulated inputs, we'll have generally some kind of valve on them. So this could be like a flow of feed or gas into a reactor, and these are generally valves that we can open and close. And then what we're going to do is we're going to, in the case of feedback control, is look at measured outputs. And with these measured outputs, we'll make these dashed lines to indicate that these are information. They're not physical necessarily. These are just information. So we're reading that in our process, we're generating 20 moles per second of component A, and we're going to feed this information into a controller, and the controller is going to make some kind of change to a manipulated variable or a manipulated input in our process. And so by opening or closing a valve, it can help us achieve some kind of desired or set point value. And that's a topic that we're going to get to in a little bit. In addition to that, when we care about feed-forward controllers, when we have no control over particular inputs, our disturbance inputs, we can also make use of our controllers by having them analyze the incoming disturbance inputs. So what I mean by that is, if we knew that there was going to be a surge in water coming into our system, and we knew that things were about to become diluted, our controller could have some logic in place to help adjust the flow rate of some feed in our system to account for that before it actually makes a change to our output in our system. And so those are for more complex processes. And so generally, when you begin a process control class, we're going to stick mostly with feedback control, but you will discuss feed-forward control later on. And to also make note of a very important topic, or very important philosophical question, is like, what is the objective? Why are we doing any of this stuff in the first place? And when we are making process controllers, the goal here is to generally achieve some kind of set point. Achieve a set point. And commonly you'll see it abbreviated as SP in your textbooks. So this can be like the temperature of an outlet stream if you needed to preheat your feed. It could be anything. But our goal here is to achieve some kind of set point as safely and economically as possible. And so that's where things become a lot more nuanced and beautiful, in my opinion. And so to actually get down to an example problem or an example situation where we can start working with a story, is we're going to look at a surge tank. Surge tank. And so in this surge tank, we have some kind of feed coming in. We have a tank. There's a liquid inside of this tank. And then we have some exit or effluent stream F2. And the tank will have some height H inside of it. And obviously we don't want our tank to run dry, and we also don't want our tank to overflow. So there's going to be some kind of set point. There's going to be a desired or demanded value of our output H in this process. And so the first step to make, or first thing to do when you are given a scenario or an example problem, is to first make note of what are your inputs in this process. And the inputs in this process are F1 and F2. And I'm deliberately not drawing any valves at this point, because when I was first learning this, it's very, you intuitively want to say, like, you know, F1 is your input and F2 would be some output, but that's not necessarily true, because F2, depending on how you draw your process or your control volume, can be an input. And so I know this is a little counterintuitive, but what we care about are inputs to our controller, not necessarily inputs in this chemical reactor that I have or a surge tank that I have. These are just inputs. These are pieces of information that we're supplying into our controller, and that's how you need to look at this. And this is kind of one of the things that tripped me up when I was first learning about process control. So our inputs are streams F1 and F2, and then the outputs, or the measured thing that we care about in this process, is our height. So our output is what we're going to be setting some kind of demanded set point for. So we're going to want to make sure that our height H is, 5 meters plus or minus 1 meter, for instance, or something like that. So we've identified our inputs and we have identified our outputs. And if we wanted to, talk to the program manager of the particular chemical plant that we're working at, they're going to give you some constraints saying, H must be between 5 meters and 10 meters in height. And we also have constraints on the tubes or the pipes. So like F1 must be less than F1 max. F2 must be less than F2 max. And so these are things that you would talk with whoever's designing this process. What do you care about here, and what am I working with? So even though it might sound really great that we can flow 10 cubic meters of water per second through a pipe, that might not be physically possible due to the diameter of the pipe and or inadequate pumps. So these are the constraints we're going to have in our process. These are the inputs, these are the outputs. And now what we're going to do is just work through a feedback control strategy. So feedback control strategy, or strat as my friends would call it. And so in this case, what I'm going to do for the sake of simplicity is say that we have some kind of valve on our inlet stream F1. And it's going to flow into some tank, the same tank that we had previously. And we're going to have an exit stream F2, so that is stream F1. And what we're going to have on our tank is some kind of level transmitter, LT. This level transmitter is going to report some kind of height. So dashed lines, H sub M indicates whatever the measured height is of our process. And it's also important to make note that is any of our instrumentation perfect? The answer is no. So there's going to be some error. So we have to account for that when we're trying to make sure our processes are safe. But there's going to be some true height inside of our tank. Our level transmitter is going to indicate some measured value of height within our tank. And then we're going to give this information to some level controller, LC, And then what LC is going to do is it's going to say, okay, given this particular height inside of the tank, I need to change the pressure of some valve that will manipulate flow F1 in our process. And if you wanted to have more to this story, why aren't we manipulating F2, even though F2 is an input? So in the case of F2, the issue here is that F2 can be a controlled variable in a downstream process, and if it is, then we have no control over that. So we're going to essentially let F2 be its own thing, and we can't account for it in our controller. And so as we continue this process, the other thing you'll have coming into your level controller is the most important thing here, which is some kind of set point value for your height within the tank. And so as we think about what's going on in this process, we're going to be having our effluent stream as a disturbance input in this process. So disturbance input would be F2, because F2 can fluctuate depending on whatever the guide downstream of you is doing. And so based on whatever the guide downstream of you is doing, it's going to change the flow rate or the height within your surge tank. And based on whatever your new height is, your level transmitter will have to read it, report that value to some kind of controller. That controller will have to say, okay, how does this new height agree with my set point height, and how much of a change should I make to a pressure on a valve to control the flow rate of an inlet stream to this process. And so this is a very explicit way of drawing it that you can do. An additional way, and the actual control block diagram way that you'll see it commonly done by process engineers, looks more something like this. So you would have your set point value HSP. This would be going into your controller, which in this case was your LC. And then from LC, you are going to be changing the pressure on some valve upstream of your process. And so this will operate some valve, which will manipulate some flow rate F1. F1 is an input into your process. And then finally, you'll have a height H inside of your system. And this height H will need to get passed through a level transmitter. And this level transmitter will be what your H sub m, your measured height, is. H sub m does not necessarily equal H, but for the sake of this example, you can assume it does. This is the control block diagram of this process, and this is a nicer shorthand way that we can better represent these kinds of processes that we have, such as in our surge tank. So in this case, just to make this very explicit, this process is our surge tank. I'm sorry, I need to write better. Surge tank, not trink. Okay, surge tank, and then because we are considering F2 to be some kind of disturbance input to our process, we would consider F2 to be this thing that comes into our process, and then we have to somehow account for an error that is created in our system due to these disturbances occurring in our process that we simply don't have control over because it's whatever the guide downstream of us is doing. And so this is going to wrap things up for this video. I hope that you guys find this stuff useful. Let me know if you have any questions, and thank you for watching.